Students, in this module, you shall learn the meaning of the commonly used terms in inferential statistics such as population, sample, random variable, random sample, parameter, and estimators or statistic. The sampled statistics are used to estimate the unknown population parameters. Accordingly, we will understand how to derive sampling distributions of the two important statistics, namely sample variance and sample proportion. We would also learn what are the properties of these sampling distributions and how are they related to the corresponding population distribution. Depending upon the population distribution and sample size, we shall know how can the forms of these sampling distributions be ascertained. We shall also learn applications of these sampling distributions in computing probabilities and for hypothesis testing and estimating confidence interval for the population parameters. To begin with, in inferential statistics, we are mainly concerned with the ideas of a population and a random sample drawn from it. It is a branch of statistics that analyzes sample information to draw inferences about the population. At the outset, we summarize the key terms relating to inferential statistics that we have learned in detail in our earlier modules. The population characteristics are called parameter, and if we do not resort to census method to obtain information, the population parameters remain unknown constants. So, if the population is infinite or very large, we rely on a subset of population known as sample or also called sample to estimate the values of population characteristics and make further generalizations. As a numerical measure of population is called a parameter, a numerical measure of the sample is called a sample statistic. I am just repeating some of the concepts which we have learned earlier so that you can in a way remember them, and it's a refresh your memory. Similarly, since a statistics is a random variable whose value depends only on the randomly selected sample, it must have a sampling distribution that can be generated with repeated sampling. We learned in our earlier module that if capital X1, X2, X3, Xn are n sample observations drawn in a random fashion from the population, then they constitute a random sample, and Xi's are independently and identically distributed random variables. So, as we draw different samples of size n from the same population distribution, the same observations will vary from sample to sample, which means each sample will give us different values which would be included. Also, if we assume that the population being sampled is normal, then each capital Xi will have the same identical normal distribution as that of X, which means the sample will have the same identical normal distribution as that of the population. The statistic or estimator, we know, is nothing but a quantity that can be computed from the sample observations. It connotes basically the procedure or the method used to combine the sample values. The sampling distribution of a statistic depends on number one, the population from which it is drawn, and number two, whether the sampling is with replacement or without replacement, and number three, the size of the sample. The two estimators we will be using in this module are sample variance and sample proportion. So, we will learn about them. The notations used for these estimators are S square and P hat respectively. In our earlier module, we have derived the sampling distribution of sample means and sample totals, and in the present module, we will learn about two more sampling distributions, namely sampling distribution of sample variance and sampling distribution of sample proportion. Now, these sampling distributions are used to make inferences on the parameters which are population variance and population proportion. Let us now define sample variance and sample proportion. What is the definition of these? The sample variance is defined as S square is equal to summation xi minus x bar square divided by n minus 1, and the summation of I is from 1 to n. And its value for the given sample is computed as S square is equal to summation of small xi minus x bar square divided by n minus 1, where I again is from 1 to n. So capital X is replaced by small x because we have taken these x values from the sample. Now it is used as an estimate of the corresponding population parameter, that is population variance in the current example, which is denoted as sigma square. We know in calculating population variance, the deviations are computed from the population mean mu, and the sum of the square deviations are divided by capital N, which is the size of the population. Hence, for a population, sigma square is equal to summation xi minus mu square divided by n, and the summation of I is from 1 to capital N. Likewise, for the population proportion P, we can say it is equal to the number of elements in the population belonging to the category of our interest divided by the total number of elements in the population. The estimator and the estimate of population proportion are defined as the number of elements, let's say capital X equal to some specified value x, in the sample belonging to the category of interest divided by the size of the sample small n. So sample size we are denoting as small n. Now therefore this estimator P hat is equal to x by n, and the estimate is equal to the small x by small n. Now before proceeding further, it is essential to understand that the sample variance is calculated using the formula, which is S square is equal to summation xi minus x bar square divided by n minus 1, where the divisor is 1 less than the size of the sample, which is because we have estimated one parameter mu by x bar. So we have lost 1 degree of freedom. Now it can be proved that S square calculated using the above formula is an unbiased estimator of sigma hat square, which is also denoted as sigma hat square, is an unbiased estimator of the population variance sigma square. So let me emphasize the sigma hat square is denoted by S square also. So the estimator that uses the divisor n, which is the size of the sample, in the formula is S square is equal to summation xi minus x bar square divided by n, is a biased estimator of sigma square. So what I am saying, and I hope you understand, is that if in the denominator you have n in the formula for S square, then it is a biased estimator. If you substitute it by n minus 1 in the denominator, then this formula of S square would be an unbiased estimator. Now, the question which you may raise is that what is the rationale for using a divisor n minus 1 and not n? As have been explained earlier, please note that in the numerator of this formula, what we have done is the population mean mu is not known, therefore it has been substituted by the sample mean x bar. So since the sample observations have a tendency to be closer to the sample mean than to population mean, the deviations which are calculated about the sample mean x bar are likely to be underestimated. That means summation xi minus x bar square is likely to be less than summation xi minus mu square or whole square. In order to correct for this underestimation, we divide by a number which is lower than the size of the sample. So if the divisor n is used, the sample variance S square will understate the population variance sigma square, and it will not correctly estimate the variability in the population. Further, the question arises why to use a divisor which is only one less than the sample size, that is n minus 1, and not any other number. So while calculating sample variance, since the value of mu is unknown, we need to compute the sample mean to calculate the squared deviations. The sample mean has an important property. I'm sure you have observed it earlier also, and that is that the sum of the deviations of the observations around its mean is always equal to 0, which means that summation xi minus x bar is equal to 0. So in calculating the deviations, let's say x1 minus x bar, x2 minus x bar, and so on, similarly xn minus x bar, the investigator cannot determine all the n deviations independently. One deviation has to be in accordance with this property. In this process, 1 degree of freedom is lost. That is, the investigator can choose only n minus 1 observations freely and not all n. Hence, the divisor used here is n minus 1 and not n. We have already learned that a statistics, being a random variable, has a probability distribution. The probability distribution of a statistic is also referred to as its sampling distribution, since it describes how the values of a statistic change across all samples of a given size that are drawn from a specified population for the purpose under study. The listing of estimates obtained across all samples is called the sampling distribution of a statistic. To understand the derivation of sampling distribution of variance, we take two examples. Firstly, when we are given few x values in the population, and secondly, when forms of the population distribution is given. The same two examples were also considered in one of the earlier modules to explain derivation of sampling distribution of sample mean. Let's take an example. We consider a simple example with a sample size n equal to 2 drawn with replacement from a population comprising only 3 values. These are x1 equal to 6, x2 equal to 8 and x3 equal to 10. Since the size of population is n, capital N, 3, and the sample size small n is 2, the total number of possible samples will be n raised to power n, that is 3 raised to power 2, and is equal to 9. Additionally, as the probability of drawing any one value from the given population is not mentioned, we will assume that all are equally likely, and also since sampling is with replacement, each draw is independent of the other. For that reason, the probability of drawing any sample of size 2 will be 1 by 3 into 1 by 3 is equal to 1 by 9. Table 1 below lists all possible sample values along with the mean of each of the 9 samples. Since the samples are independent of each other, the probability of getting each sample is same and is equal to 1 by 9. Table 1, sample values, sample means, standard variances and probabilities. So students, you can see in this table, we have in the first column the sample number, which you can see are from 1 to 9. Then we have the sample values of x1 and x2 starting from 6 and 6 to 10 and 10. Then we have their corresponding probabilities, probability of x1 and x2, which are all same from 1 by 9 for all the samples. Then we have the sample mean x bar in the next column, which is the fourth column. And we have different values starting from 6 and ending at 10. And then in the last fifth column, we have the sample variance defined as S square, which starts from 0 for sample number 1 to again 0 in sample number 9, but in between you can observe we have different values. In the last column of this table, we have calculated the variance of each possible sample. For example, consider any sample, let's say sample number 3, where the two observations of the sample are 6 and 10 with mean 8. The computation of its variance is shown below in a table, which is table 2. And in this computation of sample variance, we have taken the sample values 6 and 10 in the first column. Then we have xi minus x bar square, where we have 6 minus 8 square equal to 4 and 10 minus 8 square is equal to 4. Then in the final column, we have calculated s square, which is defined as xi minus x bar square divided by n minus 1 and its summation. So you can see we have calculated these values, which are 4 and 4, and the total is 8. It must be noted that the sample variance has been calculated using the formula s square is equal to summation xi minus x bar square divided by n minus 1. Also notice in this example, the population mean mu is equal to 6 plus 8 plus 10 by 3 and is equal to 8. And population variance is 6 minus 8 square into 0.33 plus 8 minus 8 square into 0.33 plus 10 minus 8 square into 0.33. Hence is equal to 8 divided by 3 is equal to 2.67. Now, in order to obtain the sampling distribution of the sample variance, we consider all possible values of the estimated sample variance s square, which are 0, 2, and 8, and compute their respective probabilities. For example, out of the total 9 samples drawn, 4 samples have variance equal to 2, that is s square is equal to 2 occurs 4 times. The probability of occurrence of each of this value is 1 by 9, which is equal to 0.11. Therefore, probability s square is equal to 2 is equal to ps square, in the bracket we may write 2, and is equal to 0.11 plus 0.11 plus 0.11 plus 0.11 is equal to 0.44. Similarly, probabilities can be calculated for the other two values of s square as given below in table. Table 3. Sampling distribution of the sample variance. Here again you can see we have the sample variance s square in the first column, which has values 0 to 8. Then we have in the second column probability of s square. Then in the final column we have the probability of s square, which is for s square itself, which is a simplification of these values in the second column. Further, to understand relationship of sampling distribution of variance with the population variance, we calculate the expected value, that is mean, of the sampling distribution of the sample variance. It is obtained by summing the product of each s square value with its respective probability as calculated in our table 3. So the expected value of s square, which we can write down mean of s square or mu s square, is equal to summation of s square into probability of s square, and this comes out to be equal to 0 into 0.33 plus 2 into 0.44 plus 8 into 0.22 and is equal to 2.67, which is the same as variance of x and is equal to sigma square. Note that the calculated expected value or mean of the sampling distribution of sample variance is same as that the variance of the population, that is 2.67. This shows that the sampling distribution of sample variance is centered at the population variance. This implies in repeated sampling, the sampling distribution of s square demonstrates the spread of S square values around the population variance sigma square only. Now consider the derivation of sampling distribution of sample variance when form of the population distribution is given. Example 2. Suppose 3 levels of movie tickets 1, 2 and 3 costing rupees 60, 70 and 80 respectively are available in a cinema hall. If of the total visitors 20%, 40% and 40% by level 1, 2 and 3 respectively, then the population distribution will be given as below. In this we will have first column of level 1, 2, 3, second column cost of ticket 60, 70, 80 and we have the corresponding probabilities 0.2, 0.4 and 0.4. If on a particular Sunday 2 tickets are bought, let X1 and X2 be the revenue earned from the sale of first and second ticket. Assuming independence of X1 and X2, derive the probability distribution of the average revenue earned. Table below lists all possible values of sample with their respective means, variances and probabilities. So we have table 4 in which we have sample values, sample means and probabilities. Students, you can see in this table that in the first column we have sample numbers from 1 to 9. Then we have the sample values in the second column x1, x2. In the third column we have probabilities of these, which is probability x1, x2, which is equal to probability of x1 into probability of x2. In the next column, which is fourth, we have the sample mean x bar. And in the last column, we have the sample variance S square. In order to derive sampling distribution of sample variance, we proceed as follows. From the previous table, we can see the values S square equal to 0 appears thrice for the samples 60, 60, 70, 70 and 80, 80 with their respective probabilities 0.04, 0.16 and 0.16. Hence, probability that S square is equal to 0 is equal to 0.04 plus 0.16 plus 0.16 and is equal to 0.36. Let's look at table 5 where we have the sampling distribution of sample variance. In this table, we have the sample variance, which is S square, which takes 3 possible values, 0, 50 and 200. We have their corresponding probabilities in the second column. In the third column, we have simplified this and we get the values for each of these variances equal to 0.36, 0.48 and 0.16. And in the last column, we have tried to calculate the expected value of S square, which we have defined to be summation of S square into PS square, and we have these values 0, 24 and 32. If you add them together, you get their expected value equal to 56. Similarly, the probability S square 50 is equal to probability S square takes 50 and is equal to probability of x1 in 60, x2 70, or x1 equal to 70 and x2 equal to 60, or x1 equal to 70 and x2 is equal to 80, or x1 is equal to 80 and x2 is equal to 70. On substitution of all these probabilities, we get 0.08, 0.08 plus 0.16 plus 0.16, and the sum total comes out to be 0.48 is equal to 0.08 plus 0.08 plus 0.16 plus 0.16 equal to 0.48. Likewise, we can calculate the probability of S square equal to 200, and repeating the procedure as we followed in earlier example, the 9 possible samples produce 3 values of sample variance, that is 0, 50 and 200. Out of these three values, s square is equal to 0 appears 3 times, 54 times, and the value 200 appears twice. The computation of the sampling distribution of the sample variance is shown below in table 5. The expected value of the sampling distribution of sample variance is obtained by summing the products of each s square value with its respective probability. And you can refer to table 5 for all this. And therefore, we get expected value of s square, which could be related or written as mu s square, is equal to 0 into 0.36 plus 50 into 0.48 plus 200 into 0.16 and is equal to 56 and is equal to variance of x and is equal to sigma square. If a sample is drawn from the normal population with mean mu and variance sigma square, and the sample variance s square is obtained from the sample observations, then the statistic constructed as n minus 1 whole into s square upon sigma square follows a chi-squared distribution with n minus 1 degrees of freedom. That is, n minus 1 into s square upon sigma square is distributed as chi-square with nu degree of freedom, where nu is equal to n minus 1. This test statistic is used to test the hypothesis that the variance of the population is a specified value, that is, hypothesis h naught is equal to sigma 0 square against the alternative hypothesis HA, which is sigma square is greater than sigma naught square, or sigma square is less than sigma naught square, or sigma square is not equal to sigma 0 square. Now, using this test statistic, we can also construct a 100 into 1 minus alpha percentage confidence interval for the population variance sigma square. So we find that probability that n minus 1 into s square upon sigma square lies between these two ranges and is equal to 1 minus alpha. Manipulating this inequality, we can rewrite this as probability that sigma square is less than n minus 1 into s square upon chi square alpha by 2 and nu degrees of freedom. This is equal to 1 minus alpha, where n minus 1 into s square upon chi square alpha by 2 nu and n minus 1 s square upon chi square 1 minus alpha by 2 and nu are respective lower and upper limits of the interval. For detailed discussion on this chi-square distribution, based two applications, refer to module on chi-square distribution variance test. If the objective of the analysis is to compute probability of proportions or percentage or rates of success rather than the number of successes, as in the binomial distribution, then in such cases, the sampling distribution of the proportions is considered instead. For example, proportion of defective item in a shipment, mortality rate of a disease, and proportion of students who graduated from Delhi University, etc. In all such cases, it is reasonable to assume that a binomial population is being sampled, and our objective is to estimate the probability proportion of successes, that is the binomial parameter P. Here, we know that for the binomial distribution, expected value of x is equal to mu and is equal to np, and variance of x is equal to sigma x square and is equal to np into 1 minus p, which means the standard deviation of x is equal to sigma x is equal to under root of np into 1 minus p. If the size of sample n is large, x has approximately a normal distribution and z defined as x minus np upon under root np into 1 minus p will approximately be a standard normal random variable. In effect, this approximation can be satisfactorily applied if both np and n into 1 minus p or nq are greater than or equal to 0. If a random sample of size n is selected, then the natural estimator p hat of p is sample fraction of successes denoted as ps in the sample. The sample proportion is defined as the number of successes x divided by the size of sample n, that is x by n. Since it is stated as x multiplied by a constant 1 by n, therefore sampling distribution of the proportion can also be approximated by binomial distribution. In this case, mean of ps, where s is the subscript, is expected value of e of ps, and this is equal to expected value of x by n and is equal to expected value of x by x divided by n and is equal to np by n and is equal to p. So probability of s or ps comes out to be equal to p. Now variance of ps is variance ps is equal to sigma square ps and can be written to be equal to variance of x by n. Now this is equal to variance of x divided by n square and is equal to sigma x square divided by n square and is equal to n into p into 1 minus p upon np and is equal to p into 1 minus p by n. And standard deviation, which is equal to sigma ps, is equal to under root of p into 1 minus p upon n. The standard deviation of ps is also termed as the standard error of the proportion. It must be mentioned here that this expression for computation of the value of standard deviation is used only when the sample population is infinite. A correction factor of under root within bracket n minus n upon capital N minus 1 is to be used if the population is finite. Therefore, standard deviation of p in case of finite population is equal to sigma ps is equal to under root of capital N minus small n divided by capital N minus 1 into under root of p into 1 minus p divided by small n. The difference between these two expressions would be negligible if the size of the sample is small in relation is small in comparison to the finite population size. As a rule of thumb, if the sample size relative to the size of the finite population is not more than 5%, that is, if small n by capital N is less than or equal to 0.05, we use sigma ps, which is defined to be under root of p into 1 minus p upon n. However, if small n by capital N is greater than 0.05, the finite population correction factor, which is our under root capital N minus small n divided by capital N minus 1, is to be used. Concerning the form of sampling distribution of the sample population ps, we can say it will approximately be normally distributed with a mean equal to p and standard deviation equal to p into 1 minus p by n under root if the sample size is large. If the sample size is considered large, if both NP and N into 1 minus P are greater than 10, that is NP and N into 1 minus P is greater than or equal to 10. Accordingly, the formula for Z can be written as Z is equal to PS minus P upon under root of P into 1 minus P upon N. Example. Suppose a bank manager finds that 35% of all depositors of the bank have also deposited their money in the form of long-term fixed deposits at the same bank. If a random sample of 250 depositors is selected, what is the probability that the sample proportion of depositors who have deposited their money in the form of long-term fixed deposits as well at the same bank is no more than 0.28, assuming infinite population? Solution. First, we would find whether application of normal approximation is suitable or not. Since both NP, which is 250 into 0.35, is 87.5, and N into 1 minus P, which is 250 into 0.65, is equal to 162.5, are greater than 10, the normal approximation can safely be applied. To compute Z, we require expected value of PS equal to P is equal to 0.35 and standard deviation of PS, which is equal to under root of P into 1 minus P upon N, and is equal to under root of 0.35 into 0.65 upon 250 and is equal to 0.0302. The probability that PS is less than or equal to 0.28 is equal to probability that Z is less than or equal to 0.28 minus 0.35 upon 0.0302. This is equal to probability that Z is less than or equal to minus 2.32 and is equal to 0.0102. This means the probability of obtaining a sample proportion of success to be no more than 0.28 is approximately 1%. Analogous to the sample variance distribution, the sampling distribution of sample proportion can be used to draw inferences relating to the population proportion parameters. In particular, we can test the hypothesis that the population proportion is a specified value, that is, null hypothesis H0 is that P0 against the alternative hypothesis HA is P is greater than P0 or P is less than P0 or P is not equal to P0. The Z statistics is used for this purpose if the sample size is large. Construct an approximately 100 into 1 minus alpha percentage confidence interval for a population proportion. We know that probability that Z lies between, say, less than or equal to Z alpha by 2 and greater than or equal to minus Z alpha by 2 is equal to 1 minus alpha. Replacing Z by PS minus P upon under root P into 1 minus P upon N, we obtain the probability that this PS minus P upon under root of P into 1 minus P upon N has to be less than Z alpha by 2 and greater than minus Z alpha by 2 is equal to 1 minus alpha. Here it must be noticed that the standard deviation sigma of PS is equal to P into 1 minus P upon N under root involves an unknown parameter rho. If n is large, a very small error is introduced if we replace rho by rho s. Then we find that probability P will be greater than Ps minus Z alpha by 2 into under root of Ps into 1 minus Ps upon n, but will be less than Ps plus Z alpha by 2 into under root of Ps into 1 minus Ps upon n. This gives an approximate 100 into 1 minus alpha percentage confidence interval of P. Example: in a random sample of 500 families residing in an apartment, 170 subscribe to Times of India newspaper. Construct a 95% confidence interval for the true proportion P of families that subscribe to Times of India newspaper. Solution. So what is the solution? The point estimate of the true proportion P is Ps is equal to 170 by 500 is equal to 0.34. We also find that sigma Ps is equal to under root of 0.34 into 1 minus 0.34 upon 500. This is equal to 0.0212 and the Z 0.025 is 1.96. Therefore, the 95% confidence interval is given by of P greater than 0.34 minus 1.96 into 0.0212 but is less than 0.34 plus 1.96 into 0.212. On simplification, it comes out to be 0.34 plus minus 0.0415 and is equal to 0.2985, which means the probability is greater than this 0.2985 but is less than 0.382. We understand that sampling distribution results are required to develop estimates of the population parameters, especially when time and cost involved in dealing with population are exorbitant. So in this module, we have learned that the derivation of sampling distributions of the two important statistics, namely sample variance and sample proportion, how we derive them. We have also learned that deriving properties of these sampling distributions, we have said we learned the sampling distribution of sample variance, and we have learned that it is centered at the population variance, whereas the sampling distribution of sample proportion is centered at the population variance. We have also learned that using chi-square distribution, the sampling distribution of variance is applied in computing probabilities, testing for a specified value of the population variance and for constructing confidence interval for the population variance and standard deviation. Likewise, using the standard normal probability distribution, that is the Z distribution, the sampling distribution of sample proportion is used for construction of confidence interval and hypothesis testing for the population variance. Thank you very much.